discuss the common equations used in heat transfer or heat loss with their application. So the commonly used equations are Q minus K A dt by dx. Second one is Q H A delta T. Third equation is Q epsilon sigma A T raised to power 4. Fourth equation is UA delta T. Fifth equation is Q is equal to ml, and sixth equation is mCp delta T. These six equations are very commonly used in heat transfer, or we can say heat loss calculation. Let's discuss equation one by one. So first equation, Q is minus K A delta T by delta X. In this equation, this K is thermal conductivity, A is the cross section area, and delta T is a temperature gradient, and this delta X is a thickness of the substance through which this heat is going to transfer or travel. Suppose you have a plane wall having thickness delta X. Temperature difference between these two walls are delta T. A is a cross section area and K is a thermal conductivity of the wall. So if you want to calculate the heat loss through this particular wall, in that case this is of opposite surface. Remember, this is of this particular one. So if you want to calculate the heat loss through this particular plane wall, so you can calculate by using this equation. So this equation is commonly used for the conduction. Okay. Second equation is Q is equal to HA delta T. So this equation is used for the convective heat transfer or heat loss, where H is a convective heat transfer coefficient, A is a cross section area, and delta T is a temperature difference or temperature gradient for heat transfer. So if you look at the unit, this is watt per meter square per Kelvin, this is on meter square, and this is Kelvin. So suppose again you can take an example of plane wall. If you have a plane wall and air is moving on this particular surface of the wall, so if air temperature is T1 and wall temperature is T2, in that case, and H is a convective heat transfer coefficient of the air, so here is a cross section area, so amount of heat transfer from air to this particular wall can be calculated by this equation. Okay. Now third equation is Q is equal to epsilon sigma A T raised to power 4. This equation is used for the radiative heat transfer, where this epsilon is emissivity, sigma is a Stefan Boltzmann constant, A is a cross section area, and T is a temperature of the material through which heat is going to dissipate. And this epsilon value varies from 0 to 1, and this Stefan Boltzmann constant value is 5.67 to 10 to the power minus 8 watt per meter square Kelvin to the power 4. Okay. So let's take an example. Suppose you want to calculate the how much amount of radiation can be given by the sun. In that case, so if temperature of the sun is T, cross section area is A, and cross section area is A, emissivity and sigma value is known to you. In that case, you can calculate the radiative heat transfer through this sun by using this equation Q, the number 3. Okay. Now fourth equation is Q is equal to UA delta T. This equation is used for uh, combined conduction convection case where U is the overall heat transfer coefficient, A is cross section area, delta T temperature difference. Suppose you want to calculate that heat transfer from air to wall and from this surface of the wall to that surface of the wall. In that case, you'll use this equation where U will be the overall heat transfer coefficient calculated by using the convective heat transfer coefficient of the air and conductive heat transfer coefficient of the wall. Next equation is Q is equal to ml. This equation is very interesting because if you see all other equation, you'll find delta T, but here no delta T term is there. That means during this particular heat transfer, there is no change in the temperature of the material. So where m is the mass of the substance and L is a latent heat of the substance. Okay. So the best example is, suppose you have a 100 degree centigrade water and you want to convert it to the 100 degree centigrade vapor. So whatever the amount of energy you have to provide is a latent heat multiplied by mass of the material is Q. Okay. Okay. So now last equation is Q is equal to mCp delta T. This equation is very commonly used where mass m is the mass of the substance, Cp is the specific heat of the material, unit is kilojoule per kg per Kelvin, and delta T is the temperature difference. Okay. So let's take example. Suppose you have a material having mass of the 1 kg and initial temperature is 25. So if you want, and Cp of the material is suppose whatever the Cp is there, suppose you want to increase the temperature of this material from 25 to 75. In that case, how much amount of energy is required to increase the 1 kg substance from 25 to 75 can be calculated by this equation.